Ghazal and Niayesh, thank you so much for sitting down with us today.
Thank you.
It's great to have you here.
Thank you for inviting us.
In preparing for the conversation today, I was looking at both of your websites, and I saw that Ghazal, you describe yourself there as a cosmologist, while Niayesh, you describe yourself on your website primarily as an astrophysicist. Are you able to tell us what each of those words mean and maybe what the difference is?
Yeah, how do you possibly get along when you have such different careers?
Yeah, that's it just reminded me, like yesterday, one of our friends or colleagues on Twitter posted, does your Sunday morning start with arguing about the scattering amplitude? And I'm like, only Sunday morning?
Why wait till Sunday?
I'm like, yeah, so right. So I'm cosmologist, I guess traditionally cosmologist, but it's hard to say these days what each field is really, because all the different disciplines have so many common interests, and it's always good. I tell my students right away, don't just put yourself in one box. All the amazing things that happen in science and physics is when people try to bridge over to other fields and work with other ones and see what they're doing. A lot of technical things, a lot of methodology and other things that come in other fields. Really, all of them are related to nature, and nature has the same way of doing things. So you learn from them what they have learned and so on. But right, so cosmology, I guess, technically is universe at really, really large scales beyond galaxies, and the evolution of the universe, historically how it started, like how it began, or as far as we can go back in time, to today, how it's evolving and what's going to be its fate. Obviously, the little things that we see, even as small as a planet in these scales, came out of the universe. So everything we do in cosmology will have implication for understanding the rest of the science within the cosmos, like how the initial conditions were set back in time, which gave rise or planted the seeds for everything else that grew out of it. But okay, I leave the astro to Niayesh to go.
That's an excellent question, and I don't really know. I guess these are historical differences, but as Ghazal mentioned, cosmology is a study of universe as a whole. And including its formation and its history, but astrophysics can be that, but also can be just looking at things in more detail right now. So I would say that astrophysics has a broader purview in the sense that you could get very deep in understanding the stars or molecular clouds in our galaxy, or you could get deep in understanding the early times at the Big Bang. So I would say, being an astrophysicist is like being a generalist. So my own background, when I was a teenager, I was an amateur astronomer. And when we were taught what that means, I heard the word, but I didn't know what amateur actually means. The meaning is lover. Okay, so someone who loves to do something. And that's usually in contrast to, I guess, professional astronomers who do this just to make money, like I am now. But the amateurs do it for the love of doing things or doing astronomy.
Did you have your own telescope as a teenager?
I did have my own telescope. So I started from there. I wanted to do astronomy, the study of stars and whatever out there in the heavens, just for the love of it. And the question is, when you start that way, it's hard to stop, right? So, and if you want to understand the stars, then you try to, because you love it. And if you understand galaxies, and if you want to understand the Big Bang, and it's hard to stop at any point. And that's where you become an astrophysicist, right? So your universe is your playground, and you just cannot limit yourself to studying one thing. So you study everything.
The universe is your playground. I like that. That should go on your business card.
Yeah.
I noticed when I look through the work that both of you do, there's a couple of recurring themes. One is black holes, and the other is the Big Bang, or the very, very early universe. Are they related, black holes and the Big Bang? And if so, can you tell us how?
Yeah, in a way, they're very related. It has to do, I guess, with Einstein's theory of gravity. So I would, I sometimes when I'm writing grants proposals, I would say when Einstein wrote his own theory of gravity, he also kind of, it's the right wording that I often use, something like, he didn't think it would bring also the breakdown of the theory. And I think in a way, both Big Bang and black holes are what we call singularity points of Einstein gravity, of general relativity, which is like the points that general relativity is breaking down.
And by singularity, that means that this tiny point full of
doesn't have to be
mass?
tiny, but it's a regime when things are not working within the theory anymore,
Okay.
right? So I guess technically there's different mathematical ways to understanding, and it's not clear cut at all, because when something is breaking down, how do you describe it with your theory? Because it's already like your tools are breaking, so you cannot even characterize it. But people do it in different ways. And one way to say it is, for example, a space-time. This whole fabric is getting so curved up that the curvature is getting infinite. And we know infinity is somewhere if it's not anymore mathematical. Like,
Right.
or like geodesics, its trajectories that we follow the math on, then all of a sudden they have an endpoint, and then we cannot go beyond that. So in a way, so they both are the same story. One is happening in time as we go past in time in our history, and the other one is in space. In certain points in space, we see, we predict it, but at the same time, we predict that things are not working or breaking down.
So you're using both of those types of study to figure out the places where Einstein's theory needs some improvement.
Yes, exactly. Yeah.
Interesting.
This is probably a gross oversimplification, but the way I understand it is a black hole is this mass that things sort of fall into. It attracts into a singularity. And the Big Bang seems to be a singularity that does the opposite, bursts outward. Is that a gross oversimplification of the similarities? You can say yes.
I would say no. I mean, we wrote a paper saying that.
You're saying it is.
Yeah. I mean, I don't know if it was worth a paper, but we actually published a paper, and it was in Scientific American. So it's no. I mean, actually, literally, this is true. I mean, the Big Bang is if you just turn the clock or the time backwards, then black hole looks like a Big Bang, basically. Right? Okay. So if you think about black holes, like collapse of a star into point, but if you imagine you just take that movie and then run it backwards, it just is something came out of nothing or something very dark. Now there is the one catch that the Big Bang happened everywhere, and black hole is in one place, and there lies the rub, basically. How to make that work? Right. That's, I guess, $1 billion question, if you will. So to make that work, that make Big Bang look the way we do see it, and black holes the way we do see them to be. So they have to change something, right? Right. Because black holes in one place, Big Bang is everywhere.
Can studying black holes give you insight into the Big Bang, or vice versa?
Yeah, I mean, I think so. Yeah, I think there's a lot of similarity in the things that could be happening. For example, if there is an improvement of gravity or quantum gravity, learning from one could shed light on the other one as well. Mm-hmm. But they also have their own differences. Yeah, I don't know. I feel like I would never say it's a burst. I would say it's like Big Bang is in our back, like a wall or something. We come out of it. We don't know what's happening beyond it. Right. But doesn't have to be like, the reason I'm bringing up, but there is sometimes this misconception of its explosion and things like that. And I don't know. I feel like I don't connect to that metaphor that it's explosion necessarily. It's something that, it's kind of in our going in the past, then all of a sudden we are cut back. We don't know what's happening beyond it.
Is Big Bang maybe unfortunate term because bang implies an explosion?
Yeah. So I often, like when I'm teaching my students, I keep saying, call it a Big Bang era at least. Because we know things got hotter and hotter and hotter. But I wouldn't say there was one big explosion. At least that's my way of thinking about it.
So yeah, the question is it a point in a space or is it a point in time? Right. And in fact, I mean, this actually applies to both Big Bang and black holes. There is this misconception that the singularity or Big Bang is a point in a space. So if you're far away from it, then, I mean, the Big Bang happened in one point in space, or, I mean, there's the singularity at the center of the black hole. That's not true. So, in fact, both of these are singularities are points in time, or as I said, is an era. So Big Bang is a point in time at which basically physics breaks as we know it. Doesn't matter where you are. If you are you happen to be where Big Bang is happening, then physics breaks down basically. So it's an era or a point in time. The same is true at the center of the black hole. It's not a point, but rather anyone who happens to wander across the event horizon of a black hole, they have one eventuality. There's an era at which they will be crushed by this singularity. And that's a point in time, basically. That's an era in their future.
Right.
It's like saying everybody dies, basically.
It just happens faster if you walk into a black hole.
It depends on how big the black hole is, yes. But yes, indeed. And yeah, there's not a point in a space. If you wander in anywhere you are in there, then it's going to happen to you. Right? Mm-hmm.
And what are some of the ways that you both think gravity might be modified to help improve the way we describe these things?
So the big elephant in the room, I guess, in fundamental physics, and especially in this building perimeter, is the quantum gravity, right? So we know physics has this regime that things become quantized and all of our other forces of nature can be described in quantum way. And there is this other force, gravity, that we have not been able, and we think it should also, to merge all of this together, has to be also have a quantum description. And a lot of people, like, I don't know, more than half of people in this building are working on that in different approaches. So that could be one thing, I think, that eventual. But there is also this idea, and it's not new, I think. It has always been, like, since even Newton to Einstein and other things, that there is always a regime when we describe things. You don't have to go all the way to very microscopic quantum regime to understand physics. There may be some middle ground. And coming from cosmology, I feel like this method has always worked. So maybe we don't have to, like, the way I'm trying to say it is, I don't have to start from completely scratch to build up everything. Maybe I start from things that we know, like Einstein gravity, we know works. Can we start modifying that slightly one by one? And maybe on the other side, it's going to be eventually going to reach to quantum gravity. But there's a middle way that you better understand. You're still connected to GR and the things that you understand, but slightly move away from that. And these approaches in cosmology are called modified gravities. And there is one that Niayesh and I, for example, have been fond of and worked on and thought of, which is this Coscuton gravity. We have been working on that because one thing interesting about it is that we noticed this is the minimal modification of gravity. You don't add any additional player to the game, if you say.
What would a player be?
A player, technically we call them dynamical degrees of freedom. Things that can like generate additional dynamics in your field, like an additional car or something that moves things around, right? And gravity by itself doesn't has two, which are the gravitational waves, what people call. But other things that we have, like every other thing, like baryons or electrons, things like that, you add to theories, they all have this additional degree of freedom. You add them to your theory. So these are the matter field. And then there is a general relativity. So usually the story is that you add the matter fields, and general relativity has its own gravitational waves, which really didn't play much and we didn't detect them until 6 years ago, right? Everything else we saw was these matter forces or generators, if we call them. So that this Coscuton is somewhere in the middle. It's a slightly modification of general relativity. Doesn't add additional generator, but modifies it. And we assume everything else is the matter fields that we had as before.
Could you explain the name again of that?
Coscuton. So Coscuton is a field which modifies gravity. But as I mentioned, because it doesn't have its own dynamics or generator, I thought of something that does the same thing on Earth or like in everyday life. And I thought of a plant that goes around things that have the parasite plant, which can feed off other things and even modify their behavior, but doesn't have its own root.
So it winds around another plant and takes advantage of its root system. And
it's called dodder, I guess, in English.
The Talukawa is dodder or vine. Yeah. And then I thought of what's the technical term for it? And apparently in plantology is called
botany.
Botany. That's called Coscuta. So therefore, I guess I suggested the name Coscuta, and my collaborator accepted.
Yeah. As a metaphor of this idea that it sort of attaches to an existing theory without requiring its own sort of roots.
Right. But it slightly modifies it in a ways that might have cosmological implications, but doesn't mess up other things that we don't want to mess up.
And Ghazal, I know you said that you and Niayesh worked on some aspects of this theory together, and now you've been doing some further explorations. Can you tell us about some of the things you both explored together and maybe some of the things you've continued to work on?
It's a long and winding road. It starts far, far away. In fact, Madison, Wisconsin, when Ghazal was a postdoc with the cosmologist there, Daniel Chung, and I used to visit a lot. But the story was really, what is the fastest that something can travel and not violate the laws of relativity? And you would think that nothing can travel faster than the speed of light. But it turned out, in fact, Einstein's relativity does allow for things that on paper have things that propagate infinitely fast. And it's just very counterintuitive. So we try to make sense out of it. And at the time, we realized that even though Einstein relativity seems to allow for it, you cannot actually send information with it. And basically, we started exploring that and then ended up with this theory of a field, which seemed to be doing this. That on paper, it seems that it has basically waves, sound waves in it that propagate infinitely fast. But in practice, you couldn't actually send signals with it. But what could you do with it? It turns out, as Ghazal mentioned, it could modify the gravitational dynamics beyond Einstein's theory of relativity. And what was hot back then, I guess it's still hot somewhat now, is dark energy. It was just discovered. So I guess when they got the Nobel Prize, I think it was 2011. I don't remember exactly, yeah. But it was discovered around 2000, around the turn of the century. So we kind of were halfway between those at that point. And so,
could you just briefly explain dark energy and what changed when it was sort of discovered in the 1990s?
Absolutely. So there's been this big puzzle in Einstein's theory of relativity and Einstein's gravity for over a century since it was discovered. So in fact, Einstein, when he first wrote down his equations, he added this constant called the cosmological constant, and he needed them to keep the universe static because otherwise he wanted to either blow up or crash. And he wanted to tame it, so it just basically added this thing as keep it there. it turned out that that wasn't a very effective way of doing it. And he later confessed that it was his biggest blunder to actually add that there. If he hadn't, he actually would have predicted the universe cannot be static. And Hubble later discovered that the universe was not static. And however, that the cat was out of the bag. So this cosmological constant that Einstein introduced never really disappeared. So it was always there. People always knew about it. And it took another 100 years for people to actually discover a sign of that or something like that. The problem is it's just such a big surprise because it doesn't fit anything else. So there is this thing that looks like a constant. It has energy, it has pressure, this has negative pressure. So the only thing that we know that does have negative pressure. And its scale is smaller by orders of magnitude than anything else we see around us in the standard physics. So it's such a bizarre thing that we kind of, physicists had a field day with it. I guess they're still having, they invented all sorts of things with all sorts of funny names to kind of model it. Unfortunately, so far, the evidence doesn't show that necessarily it's anything more than a cosmological constant, but it could be. And at that time, basically, one of the possibilities, we thought that, okay, so, I mean, Einstein theory has been so successful. Maybe it's a cosmological constant, but what is the next simplest thing that we could come up with? And this Coscutan was an idea, and it's the next simplest thing in the sense that you're not adding anything to Einstein's theory of gravity, and every other possibility that people have studied, you're adding additional degrees of freedom, additional kind of beasts into the theory. And this one was not just the same beast, but just a slightly modified behavior. So that was the beginning, and we kind of explored the possibility, which is still there, that dark energy could be type of Coscutan. We haven't confirmed or ruled it out yet.
And dark energy, correct me if I'm wrong, is it's what's making the universe expand at an accelerating rate. That's
right.
Absolutely.
Yes, exactly.
Yes.
Yeah. Basically, cosmologists love the term dark. Whatever it's a puzzle, we put a dark in front of it.
I noticed that regarding dark matter.
Yes.
Yeah.
You have now dark radiation, dark sirens.
And does it essentially mean unknown? It's an unknown quantity. We don't know what to call it aside from dark.
Although, like the dark sirens are slightly different, but most of the time,
different times means different things, but for dark energy, it's probably as dark as it gets. So it's it doesn't seem to be interacting with anything. We don't see it. So that's a term that I don't know. I think Mike Turner first invented that term, but I mean, people indeed. What was discovered was cosmic acceleration, which was very surprising. You would think gravity is attractive. So if the universe is expanding, it should be slowing down because of gravity. And lo and behold, when they measured it, they realized it's speeding up. But it turns out they already had a model waiting like for 100 years to explain it. As Einstein's
we are not sure yet. Like they're still like, you talk to string theorists, like for 5 years, I think when the astrophysicists started noticing it, they were still in the camp that no, in the string theory, there's no such thing as cosmological constant. Like it cannot be. And then like once they observe it, and then all of a sudden we started, actually we have, how about
10 to the 500
of them in our theory, and we're like, now what do we do? We get rid of all of that.
So cannot quite decide it's a 0 or 10 to the 500.
Ballpark.
Yeah. So now there are a couple of camps. Apparently, some are like there are a lot of it, and some are like, no, we cannot have it.
Yeah.
But what is for sure certain is that it's observed. Something is there. Right?
Yeah. Is one of the goals to try to explain it with as few new variables, as few complications as possible, and then add them?
For us, it is. Yeah. From our point of view, like phenomenological, I guess cosmological. I guess our approach is sometimes called bottom up. Their approach, starting from very fundamental theory, is top-down approach. So we are working our way. It's going up. They're working their way.
Hoping to meet at some point.
I wanted to ask you. You've both studied the early universe shortly after the Big Bang. Is that research related to dark energy? Can we learn anything from the origins of the universe about what it's doing now, its expansion and acceleration?
Because a lot of it is really math, right? At the heart of it. And the mathematics that is describing the same theory, gravity. So what applies back then should be applicable today as well. Some things may be more relevant back then than they are today, because energy is where the universe was much hotter. So than today, it's much colder. But at the same time, the rules should be the same rules. So whatever, that's why it's very easy. And it happens so very often. We learn something that can be done in early universe, and then a few years after, we try to apply the same thing in late universe. Oh, this technique worked there. Like in that context, can we do the same thing now in late universe? And there's so many examples of that.
But I guess just to follow up on that, so there's the leading, the most popular theory for the universe is called inflation, which in fact is like a dark energy, but at like souped up or on steroids at much higher energies. So we see it happening now, but it's proposed that something like that with much higher rates was happening early on. So that's one possibility. That could be a similar scenario, of course, on very different scales of happening, acceleration of cosmic expansion. But beyond that, there could be other possibilities. If you have like a cyclic scenario of the universe, then in fact our future is our past. So what's happening now, like the cosmic acceleration, could be setting up the initial conditions for the next generation of the universe. So depending on the scenario, there could be even more close connections between early and late universe.
Could there be future Big Bangs?
There could be, in a cyclic scenario. I mean, Roger Penrose is a big fan of that, as our previous director, Neil Turok and Paul Steinhardt. They had their different models of cyclic universes. And so that's certainly one possibility that people have studied. Yeah.
And is it possible that this Kaskutan model would support some of those scenarios?
To be honest, I haven't. I have not considered that, but because it's kind of like a puzzle. I have been focusing on a particular piece of it, just going from one contraction to expansion. It seems so. Let me back up a little bit. So if you want to have right now, the universe is expanding and accelerating. So if I want to go back into the beginning, so what scenarios could I imagine? One is that maybe then expansion enters contraction, and then again expand. That's one possibility. But there could be other things, like expands and then out of it something bubbles out or tunnels out, and then again. So depending on this, then you have to work on a different scenario for that transition to happen. But one thing I am working on, it maybe this, at least we can figure out how you can go from a contracting universe into expanding universe, which is not an easy task. Like general relativity doesn't allow it, because you violate certain energy condition, which if you do that, then the things break loose, a lot of instabilities, and theory again goes through violent behaviors. But that's where right now my focus, in fact, one of my program is. It looks like Kaskutan can make that possible. So you could make a universe go through a contraction, and then we call it a bounce off into a expansion. So in that context, it could fall into a bigger picture of cyclic universe. We haven't expanded too far. We are now focused on that particular phase of bouncing. But certainly could be applicable to that bigger picture.
Yeah, and I think your answer leads to maybe a bigger question that when you're trying to, I guess in the end of the day, approach quantum gravity, there's so many different ways to approach that. And you're talking more about modified gravity, and there's so many ways within that. So we have a really good question that was sent in by a master's student, Anna Knur, here at the Perimeter Institute. So let's play that question.
How would you describe each other's approach to doing physics? Would you say you have different styles of research?
Long pause as they consider their answers carefully.
Should I go first, or do you want to go first?
My answer is yes. That's
We would request a more elaborate answer.
Maybe I can.
Yeah, I don't know.
take turn.
Is the correct term cynical, or someone who is like, I don't know. I have this approach that I question the validity of everything. And Niayesh has this approach that, no, of course, that's the way it is. And I'm like, no, sit down, let's write it. So it's a lot of back and forth argument. Like I am like, I don't know, I always like, no, there must be something wrong with it. Let's check this aspect. Let's check that aspect. He's more optimistic and like taking a leap to next big thing. And yeah, universe goes from this and then cycles to that. And I'm like, no, there's a lot of things can go wrong. Let's work it out.
Is that an accurate depiction?
I think that's very accurate. Yes.
But is it useful to have both of those perspectives when you work together on something?
I think so. Yeah. Like I'm trying to,
It sounds like two halves of sort of one brain trying to, check each other.
Check and balances, I guess, or something. Yeah.
Yeah. I think Ghazal is very good at kind of identifying the details that are important and need to be understood to kind of for the whole picture to make sense. So my own approach is that usually I have just some very big pictures that this should work, and then I say, so you need to fill out the detail, and then either I ask someone to do it, or I just sit down and count those hours. And sometimes the details will be filled out. More often than not, it doesn't, and just because the whole picture was wrong sometimes, or maybe it just takes much more time. So, but that's that's the approach which I don't know. It's just worked for me. But I think it's good. It's very good that Ghazal can identify all the places that it doesn't work. Yeah.
Does that apply in life outside of science too?
You can imagine.
Yeah, he's like, let's have kids do this. I'm like, wait a minute. It doesn't work that easily. I have to do this research. You have to check that.
Yeah. Does this apply to the Kaskutan model? Ghazal, you're still checking a lot of different aspects of that, and really
exactly. Like I am that way. Like it takes me longer to make sure I feel confidence, even though like we had, I think by now 3 papers out, I'm still like, okay, next, let's do one additional step. Check this thing, check that thing. And I think to his credit, he does a lot of that too. Like he has done it like, and it's, this is very unique because not most physicists are expert in one particular field, but Niayesh does this thing that he comes up with a theory, then he checks the data and goes to talk to the statisticians or like simulationists and does these things. But
it does seem, Niayesh, especially going through your website, the subject areas that you're interested in, it gets to be a bit of a long list. There's all sorts of subject areas. Can you explain, is that just have you always been curious about all sorts of different aspects of physics?
Yeah, it's kind of this thing in your head. You don't, I guess you start exploring different things as a kid, and then at some point you tell, there's a switch there that says, okay, that's enough probably. You want to stop somewhere. And I maybe that's missing in my head, that kind of keep exploring. And the thing is that, the more tools you have and the more experience you have at this thing, you think you can understand more things, which doesn't work, to be honest. But somehow that hasn't sunk in. That if your experience doesn't necessarily lead you to, it doesn't help with solve things better. There are more and more problems that need to be solved, but nonetheless, when I see a puzzle, be it what happens at the center of the black hole or at the Big Bang, or it could be, dark matter halos, cosmic acceleration, or how COVID spreads across the globe. It seems that there are similar types of, when I look at what's happening, I can see all the similarities. Like when we study dark matter and dark energy, and then we study the spread of COVID, neither of them you actually see what's happening. We don't see the viruses going around like one by one, and we don't see the dark matter particles. But what we do see are the consequences. We see the shutdowns, we see the hospitals filling up and things like that. And we see formations of galaxies. And then that's where I see the similarities. And it's kind of, it's hard to ignore those. That's the problem.
Yeah.
I kind of lie at bed, awake at night. Says, okay, so this is very similar to that, and I cannot just fall asleep without kind of pursuing that, and that's what happens.
Yeah.
And are there certain models or ideas from your work in astrophysics that were particularly helpful when you were studying this COVID-19 modeling?
Right. So my PhD was kind of an interesting story, which, as similar to the rest of my academic career, had lots of different things. But one thing in particular was very similar to COVID because so I was interested. My supervisor was working on cosmic microwave background. But then we also had galaxy surveys out there. Of course, galaxies, people see them with telescopes, optical telescopes, cosmic microwave background. You have the satellites that see microwave. So different things. And for the most part, they are different things. They see different things. But then what I did was I actually looked at the correlation of the two signals. And then it turns out there's a tiny fraction of these different things that are same. So there's some is the effect of the dark energy, the cosmic expansion. Some was the effect of hot gas in the microwave background. And it turns out that these are the things that you couldn't see on each of these surveys on their own easily. But if you combine them, you could actually kind of get these tiny signatures out through the combination. And it's actually, that's what I did for my PhD. And it wasn't it was not very much off mainstream. So I mean, I was one of the first people who were doing it, but now everyone does it. But and if you just think about it, you can do this everywhere, right? So we see very different things for very different reasons. But if you can combine them, you can learn something very different that each of those data sets cannot teach you. Mm-hmm. And I realized that basically that's technique, which I guess the technical term for it is cross-correlation, that can be used kind of widely for example, in the pandemic, that you could use various measures of people's activity and the spread of the disease, and then through carefully designing cross-correlation studies in a space and time, which is what similar to what you do in cosmology, right? We could learn about the various properties of the disease. For example, how much the change in people's if people are getting vaccinated and at the same time they're having lockdowns, and at the same time some people are getting immunity from prior disease, how can these three interact with each other? Because they could all have similar consequences. Yeah. And this cross-correlation is the way to do it. In fact, that's how I did. I could separate the effect of dark energy, the effect of hot gas, and the effect of radio sources, but through this cross-correlation study. So if you have a lot of data, you could do it, basically.
I saw you mentioned in one interview that data from the COVID pandemic, there's a lot more of it, and it comes a lot faster than from black holes and from the Big Bang. Like, was it sort of a gift of data for you that you had these huge numbers?
It's the curse. You would think it's a gift like for a week, and then it's the curse.
Too much data?
Too much data. Too much, too fast, too many things happening. And,
no, it's the other way around, right? We are losing the data. It used to be, I think it wasn't quite like that, because you were telling me, and that was part of the problem. Like, I kept telling him, tell me about Waterloo. Like, what's the economy? And he's like, no, we don't have data in Canada. All I can tell you is what are the counties in US, because the data was abundant there. It could cross-correlate between all different counties. How many there were? I don't know, 30, way more than 3,000.
3,000
counties where each had their own data set. You can track them.
Yeah. And essentially you made sort of a dashboard where you could input factors, say weather or
lockdowns
and vaccination rates. And then it was sort of a predictive model of spread.
That's right.
One conclusion I saw that surprised me until I heard an explanation was that the effect of weather, or at least the indirect effect of weather, hot weather and cold weather. Could you explain what you saw?
I mean, these are all the things that come out of the data. I mean, I wish I had a better understanding of it, but it's, in fact, somewhat similar to what Ghazal was talking about, that you don't necessarily understand fundamentally what's happening. Like same with quantum gravity, you don't necessarily fundamentally understand what's happening. But if you have a good enough data, you could have an effective description. And what we did is we got this effective description of what's happening. And basically, the conclusion was that if you look at a spread of COVID across thousands of counties, across thousands, well, I guess you have hundreds of days now, there are these factors that are at play, and one of the significant ones are weather. That when things get colder, where the temperatures dip below around 15 degrees Celsius, then COVID spreads faster. So, and then this is in addition to all the other effects. So if you include the effects of mobility and vaccination and everything, so that those are of course there, but in addition to that, there is this effect. So, and I mean, I guess this is probably the least surprising one because we had seen that for other prior viruses like flu and common cold. In winter, they are more severe, and that's what we got. Yeah, absolutely. So. But then, yeah, so there are all of these. The thing is that there is no one factor that could, and this is kind of one of the problems that I kind of keep rolling my eyes whenever I see an analysis of COVID anywhere, which there are so many of them, it's hard to avoid them because they just kind of say, oh, look, this place, this country did this, and then they're doing well, and then this state did this, or the city did this, and they're doing so well, or maybe they did this and they're doing so bad. And I mean, I looked at, as I said, hundreds of thousands of data points, and there is no one thing.
Right.
That, yeah. So all of these happen in concert. There are various things, and that's the way science works. That we need to. I don't really know how, but if we can teach people this in any way, either at the school or through outreach, that science is understanding of various things that happen at the same time in face of uncertainties. That's the way science works. You cannot say with certainty that if you do this is going to happen. That never really happens.
Yeah,
Right.
And another thing I keep wondering when I look at this idea of combining these different kinds of data, as you were saying, you have a lot of data, but you're trying to combine different aspects, right? And I guess some of those aspects might have more data than others. So something that maybe still could be important for modeling something maybe could be harder to collect data. So one in particular, when I looked at this online portal that you made, is the number of people wearing face masks. I would assume this is something that's probably quite hard to measure.
Yep, that's it's so we had a way to do it, which is the number of people who were Googling face masks, which was not the best, but and one of the challenges, I mean, actually, not just challenge, part of the scientific method is not just to understand your data, but understand their errors or uncertainties. And that's not just for your data, but also for your models. And so we have to understand our model, we have to understand our uncertainty in our model, and we have to understand our data. And so those were all the challenges. And these are challenges that we deal with in cosmology and we deal with in COVID. So I try to kind of import those techniques in from cosmology to some extent. But yeah, the thing is, you can never only focus on your model or your data. It's all uncertainties all over. So uncertainty is the real lead, the real boss, actually.
Right.
Yeah.
Can I ask us to go a little bit back in time? Because I'm so curious to know how and when you met.
Okay. You said you met me first, right? Okay.
No, I think you said no. You said you heard me say something, and then you didn't have your glasses, so you couldn't.
No,
see
but I'm
me.
talking about before that, right? In high school.
Oh yeah, high school. That's right. No, that's true. I did. Yes.
Oh, I didn't know there was a high school.
There was a high
vague. Vague meeting, as in quotation.
Yes.
So apparently there was this national competition for math and computer science and things. And
Iran?
In Iran.
Yeah.
So I think which competition had you passed the first round?
I was in physics. Oh no, I was in math. I think it was in math. Yeah.
Anyway,
yeah.
So each province, for example, you do the first round and then you get to the next second round. And we both have made it to the national level. And then they took us on this 1 week competition trip that now from all provinces, people go to do the second round. So I was competing in math and computer science.
Where was that? contest?
The contest, the second round was in the city of Mashhad. So there weren't, I guess, many women who in the second round got prizes and stuff. And apparently Niayesh says, I remember a couple of girls went up there and got a trophy. I'm like, oh, that was me. So you met me.
Yeah, I didn't get anything in that prize, in that competition. Yeah, no.
So anyway,
How many students were in this competition?
The second round, I think maybe 100 in each topic.
Yeah,
and then
there were some going probably 100, 150,
50.
I would think. So yeah.
So you both already had a strong inclination towards science and math at that point?
Yeah. So I had a good study group in high school. There were especially another friend. We really loved to do math problems. And I didn't think I was good at computer science. So that one I just participated for fun. No, actually, which way it was? I think I did it the other way around. I wanted to compete in computer science. The math I participated for fun because now I remember. So they had the days of the tests were alternating. So the day we had the computer science test, the night before that, me and my friend was like, okay, let's sleep early. Tomorrow we have to be focused.
Yeah, I don't know a lot of people who say, do you want to go out and have fun by going to a computer science contest with me? It's an interesting definition of
I don't
fun.
know. And then the math one, I would go like, oh, let's go do it. And then
The math one was for fun.
Honestly, like, so there was, because there's a funny story about it. So at the math one, you might have heard of Maryam Mirzakhani.
Yeah.
So she was competing from Tehran and I was competing from this other city. I'm like, look at her. Obviously, she had already won the math gold medal internationally the year before. I'm like, what am I doing here? So she was doing and sitting like in the exam. I was looking at her and I was sipping my snacks and stuff. The little I know, I did way better in math. I won the silver medal. I'm like, oh, I should have tried a little bit harder. But anyway, yeah. So,
but that was just a sort of fleeting meeting.
And I guess, Ghazal, you don't remember meeting Niayesh, but Niayesh, you remember seeing
Yeah,
Ghazal.
I was in the auditorium, like somewhere down there, and she was on the podium or on the scene. So that was that. I think Ghazal said you heard me. I was kicked out. I was kicked out of the class.
Yes. So there was a modern physics course, and then I didn't bring my glasses that day, so I couldn't see very well the board. So I sat in the front row, and then in the maybe 20 minutes into the class, apparently some students entered the class, and we had this older professor who was very much into like etiquettes of the class and things, and he got really upset. Started, "What are you doing? Do you know?" Like started kind of yelling at you, I think. Like,
what were you doing wrong?
Because I was at another class. I was trying to take so many. That was like my first semester in college, and I was trying. Let's just like everything else I do. I wanted to do everything, and there were different classes that were overlapping. And somehow I decided that maybe I could just miss the first 20 minutes of one class. But then my professor who we turned out to be great friends afterwards, but he kicked me out, and I think Ghazal.
So I just heard like there's a boy there, and then some of my friends said, "Oh, this is the guy who won the physics contest Olympiad." I'm like, "Oh, like who's that guy?" I'm like,
who's this guy getting kicked out of my class?
And then was it shortly after that you actually started talking?
You said you came to my tutorial session. Right?
Yeah, she had a tutorial about the shape of a string. If you take, I remember she solved for the students, including me there, what is the shape of a string if you hang them from 2 points? And same as cosine hyperbolic. So
and you were teaching that, Ghazal.
Yeah, so I was like a second year undergraduate student, and the first year undergraduate approached us and said, would you hire your students want to do some problem solving sessions for us? And I said, sure, yeah. So I'm I volunteered to do that. And I thought this is a very fun problem to solve. The math is very nice and beautiful. So I was solving that on the board for them.
And you didn't kick him out of your tutorial.
No, I didn't.
No, she was a nicer
Show up on
teacher.
time.
That I don't remember.
Yeah, I probably thought, what is he doing here?
Yeah.
And so this was undergrad, right? And then
Undergrad.
so what happened from there?
So then the fourth year, I think I saw him here and there. Niayesh didn't take actually many undergrad courses anymore. I think at some point after the first semester, he decided to just go directly to grad courses and gave up. And then right. So there was we had one of our professor was planning to organize an international workshop in one of the islands in Persian Gulf. And so therefore, in a year before that, in preparation, he had started these cosmology courses and cosmology. And he was a GR person, general relativity. His specialty was general relativity, but he wanted to do the workshop on cosmology and said, I'm learning myself. And he recruited some, I guess, graduate students, right? And maybe Niayesh as well. And I think I heard about that. So I signed up for the cosmology class. Niayesh already became the TA for me. That was not the other way around. There's another story about that, and then meanwhile, another...
Which you're going to tell us?
Which I really still very upset about it. I'll get to that soon.
Yeah, I think just the moral of that story is that... yeah, so if you are a TA, you shouldn't date your students.
Yeah. So meanwhile, another professor suggested another interesting project based for undergrads, and he started the cosmology project, and I think you and I...
Anyway, there were lots of different...
lot of things. So we got to know each other, and then gradually we started dating. But then meanwhile, he was my TA in this cosmology class. So the story that I'm upset about is because they give a midterm. He's proctoring the exam. And I'm a very a slow writer. I can never write in time. So right now I know he being here, I know probably had a disability. I should have asked for extension. But anyway, back then, so the exam period ended, and halfway through, there's a lot of problems I haven't solved. And she's like, okay, time's up. Let's took my paper and went. And I had another friend good friend, took the course. And then the day, a couple of days later, they posted the marks. And I was the first mark or second mark or something. And then this friend of mine teases me and says, haha, of course, you're dating him. I got really upset. And then I talked to him and I said, oh, did he say to that? Because I gave him extra time. I let him take the exam home and bring it the next day. And I'm like, what are you talking about? Anyway, yeah. Then
so you didn't get special treatment. Somebody else.
No,
did.
I even got the worst treatment than the other guy. I'm like, oh gosh.
Yeah.
And yet here you are.
Yeah. He should have been disciplined for that TA.
I should have been disciplined. Yes, I guess I was a very bad TA.
But I relate to you, Ghazal, because for me also writing in time was really hard, and I maybe also needed to ask about something, but I just can remember after exam season I would carry all the stress of the exam in my hand, I think, and then I would need a couple weeks after exams to recover. My hand would just be so tense from trying to write everything that was there so fast, and it's really stressful. And then so it was graduate school shortly after that.
Right. And then we went to this cosmology workshop in Kish Island, very beautiful island. If you ever go to Coral Island, is it one of the few coral islands in the world where the water is so clear, it's all the beaches is just corals. And my supervisor was there, and I guess
future supervisor,
PhD supervisor. And if you ever get a chance, you may want to interview him. He's really nice, interesting person. He's anyway. I'm getting distracted.
Sorry, what's his name?
Brandenberger, Robert Brandenberger. So he would back then, like he was very willing to go to this, like to Brazil, to Iran, to other places and recruit graduate students. Like if he saw a good graduate student, he would support them. So we met him there. He was very impressed with me and Niayesh, and we said, well, we haven't applied, but we know going to US is extremely hard for Iranian student. He said, okay, I'm gonna go there, and you send your application. We'll see how things go. And we didn't really have much hope because not many Iranians would make it to US. And it's a very hard, even to this day, it's a hard decision. If you go there, you're trapped for a few years. You won't see your families and a lot of other complications. But anyway, he went there, and then we both applied, and we got admissions. In the middle, had to do a lot of things. We had to go to a third country to do GRE exams. We had to apply for visas a couple of times, got rejected, then go to another country, apply again. So after a lot of hurdles, we finally got the visa and admission.
And then we got married
And then we said, okay, we were dating and everything for a couple of years then. But then we said, okay, we are not going to see our parents probably for a long time. And if we are planning to get married, let's do it and celebrate it with them before moving on. Which I think was a good thing. Like everybody celebrated. And then, we moved to US.
And then we disappeared.
And then we okay, got married, bye.
Now you're married. You're both at Perimeter Institute and you have kids. I wanted to bring up your kids partly because of the book that you wrote. Can you tell us a bit about the book and why you wrote it?
Yeah, so my son was, as it is probably with a lot of children, like they get really obsessed about something. Like one day it's the what is it, the Sphinx in Egypt.
Sounds like something they got from their father, maybe.
Yeah, maybe. Then for a couple of months, we are just looking and reading about Sphinx and Egypt, and our whole future is planned to move to Egypt to live next to the pyramids. And then there is the human body again, there's a phase of that. And then there was a phase of the black holes. Like he was obsessed, what is it? What is it? And then I'm like, okay.
Did he know about them because of what you do for a living, or did he see something else?
No, I think overall space is one of those things that children, maybe it's the impact of the media and outside world, or maybe it's kids are
really...
must
have seen it somewhere. Right?
But it's not from you two are arguing over singularities.
We don't.
No, if anything, we probably have the reverse.
We try to keep them protected from hostile environments.
Yesterday, our younger son was watching something about the space on YouTube, and Niayesh was like, I don't want to listen. There's so many mistakes in that video. I don't want to listen.
And how old was your son when he started getting interested in black holes?
So he was almost 4.
Wow.
Yeah. So at that point, I'm like, okay, obviously it's too soon to teach him any science, but still there's maybe I can do a small, very short story to include not scientifically wrong things in it, but at the same time be just a story, just keep his mind entertained, read it to him.
Well, it's great too because you have this guide for parents or teachers as well, right? That goes a little bit deeper, so you can give the book to the 4-year-old, and then the parents can learn a little bit more.
I think so. I think I learn a lot because of my children in other topics that are not my specialty. When they become interested in something, and then he brings up the book, and then I get curious. Okay, what is the actual thing that is happening? Is we are learning about this country or geography or this plant or something else. So yeah, I feel like it's a very good bonding experience and educational experience for parents and child if they read together things. So that's why I included the guide. So if they're reading about it, they also learn a little bit about the science behind it. That might be.
For the people with who are watching, could you show us it's called Bella the Black Hole?
Yes, Bella the Black Hole.
Would you mind reading us a little bit?
Okay, sure.
It's I want to say it's also beautifully illustrated, and I believe it's illustrated by a relative. Is that right?
Yes.
So
Niyayesh's cousin, Nasim Abayan, and she, in fact, worked in Toronto.
Okay.
And yeah, she
Yeah.
I like her work. And
She's
stuff.
an illustrator. Yeah.
Yeah. And it does have a little bit of a Middle Eastern theme into it. Like, I feel like.
Yeah,
So,
it does.
yeah.
Mhm.
Like you said, it's scientifically accurate, but it's obviously not scientifically detailed. So that's a challenge to write for a child
Exactly.
to comprehend without getting the essential truth wrong. Right?
Yeah, and I'm hoping, like, even as they get older, they look back at it and like, oh, what did she mean by that? Maybe I have to go read a little bit more about it.
Yeah.
Right? So, my name is Bella. I am a very shiny and hot star. Do you know another star? Yes, our sun is a star too. I'm younger, but much bigger than the sun. Gravity wants to squeeze me.
I like that that's just one page in itself. Like, what a beautiful condensation of an idea. Wants to squeeze me.
It's not easy to condense these complicated things into one phrase like that.
We all had them with the action motions that we had to squeeze the child at that point.
Oh, is this a participatory
yes,
book?
I remember that's how it went. I know it's been a while. Yeah.
But the pressure from hot gas pushes me back. At last, I get tired and gravity wins.
I think you should maybe not finish
Leave
it.
the rest of it for the
That's the origin story.
A cliffhanger.
Yes.
Yeah, cliffhanger.
So I'm not going to spoil the end of it, but I guess from the name, there's a black hole appearing at some point.
Somewhere, yeah.
And what was your son's reaction to this book?
I think he really loves like those action motion, like the pushing and gravity and like and then
there's spaghetti in there.
Spaghetti.
Can you explain the spaghetti reference? Because it does actually, spaghetti has a scientific sort of black hole meaning.
Right. So spaghettification, that's the term, I guess, that as we get pulled into a big black hole, stellar black holes, right? Is that the
well,
one?
it depends on how close you get. Right.
Yeah, and then it's not. People have this idea that they will just like go inside nicely, but that's not how it's gonna happen. Unfortunately, we're gonna. Does the stellar, interstellar have the? They don't. They go in that
The movie.
Yeah, that they keep turn.
They have a very big black hole, so
okay, so
this
that
is a
one
very
they just
mild
went in.
effect.
Like
Yeah.
thinking they went in without anything
I don't
happening
think they
to
got
them.
spaghettified.
No,
though.
they didn't, right? But in these ones, you get pulled and get the tidal forces and stuff. You start to get stretched and then become like a spaghetti. So there is not really much of you that's going to make it inside.
It's nice that you could write about something that, that is that idea is kind of scary, but in the book, Bella is this lovable character who's explaining her life cycle,
and then you can see inside the mom or parents' mind that what they're struggling at that point, like between the different foods, like eat the broccoli but no spaghetti.
And Niayesh, I know you also have a book that you're working on, and I know we're not going to give away too many details, but do you want to say? Is there anything you want to say about that?
It's going to be a slightly more elaborate version, but more focused on the Big Bang and various ideas and characters that are involved.
Just to be clear, not a kid's book, right? This is a popular grown-ups.
I think kids at heart could could read it. Yeah, so this is going to be a popular for popular audience. I hope teenagers could enjoy it, but we'll see. That's I don't actually know how much of it I can give away. I feel like I can hardly control myself, but it's going to come out hopefully within a year or so, and it's more about the Big Bang and various people and characters involved.
Another cliffhanger.
Another cliffhanger. Yes, there.
First, we have to finish reading Bella the Black.
Yes.
That's a prerequisite, I guess.
Yes, exactly. We should start with that, and then we're gonna build up our way to the other one.
Yeah.
Slightly longer book than this one. Yeah.
Well, another thing I really want to make sure we ask you both about is that you're both quite involved in outreach and versed in writing books in other forms as well. And you're also both advocates for equity, diversity, and inclusion, EDI, within academia. For example, Ghazal, I know you're involved with the Supernova Foundation and a few other initiatives. Can you maybe tell us a little bit about some of these initiatives you're involved in?
Of course. So, yeah, EDI is quite close to my heart because, I mean, the journeys I've gone through to make it to today, still being able to do research has been, as I mentioned, alluded to, it hasn't been easy. And
you mentioned you were the one of 2 women on stage in your high school contest.
And there is there is a pre-immigrant phase, which I had to deal with certain things, being a woman and being in science and being in math. It had its own hardship. And then being a Middle Eastern from a certain country in North America, we had to deal with another set of problems. And then having a two-body problem, which is often a lot of women physicists have to deal with. I think a good proportion of them have two-body problems.
Can you tell us what that phrase means for people who might not know?
Oh, yes. So for some reason, physicists, female physicists, also their partners are also academics. And therefore, because finding 2 academic jobs in the same location is quite hard. So we refer to this as a two-body problem, where one body finding a second job or having 2 in the same institution or at least same city is quite hard.
I mean, finding even 1 is hard, so finding 2 can be nearly impossible.
Exactly, yeah. And we have been through so many things over the years. Like I had to, even pregnant with this guy, this little guy, the older one, the closest job I could find here was in Buffalo. So pregnant, I had to travel back and forth to border,
Really?
crossover, come back, and
was it like 5 days before he was born that you crossed the border? Or
yes, also crossover. And I'm glad I didn't know this, but things could get complicated if he didn't come right on time.
Right.
Because I was like, oh, it's no big deal. If I'm having a delivery, I'm just going to go to the hospital, right, wherever. But apparently now I know that could be risky, driving alone and going. But anyway, and I mean, again, I think two-body problem, having families in academia, all of this have a lot of challenges. So marginalized community have that on top of everything else as well. So what can we do to help out? I mean, I feel like I might not be able to move mountains, but even if I can help one person to move along, that's my goal. I've done something, right?
Yeah.
The little things we can do. And one thing that we noticed, a lot of places, a lot of challenges are easier to tackle if you have a network, if you have a friend who is there with you and can hold your hands, and especially if they're a little bit ahead in your road and can tell you, I faced the same thing. Don't doubt yourself. You might be able to do that. Or there's this strategy, like, why don't you talk to another person or put you in contact with someone else? So this Supernova Foundation came out of this idea. The original story was that another friend in Ames, the director of Cosmology group there, used to organize undergrad workshops in Mauritius Jedi School. Was it? Yeah. So we went for one of those, similar to what my supervisor did for us, I guess. And then he, after a couple of years, I think we went there in 2013 and 2015 or 14, he contacted me and a few of other women who had participated and said, you know what I'm noticing in this small scale community is that the students that come to our workshop, we have seen some of the men go to graduate school, but none of the women have. Is there anything we can do? And so 7 of us, 3 from the people we met in the workshop, Michelle Lochner and Valeria Peteronis. Michelle is in South Africa. Valeria is Peterino is now based in Paris, France. So we volunteered to start something. I came back, to my friends at Perimeter, Nusimio, the late Nusipio, what's her last name? Swani, Chiamaka Okali, and Sarah Chandera. I recruited them, and René Lajek, who is now professor at Toronto. 7 of us started with 8 mentors. We said, just do whatever we can do. Like every couple of months, let's talk to these women, how they're holding up. And it was not that easy. We didn't have the experience of doing this kind of work before. But at least one of those women made it to graduate school and followed up and went on to pursue her career or dreams in physics. And then we thought about, okay, if there's only 7 of us, what if there were more of us? And we could have other women who can help us out. And out of this came this story of Supernova Foundation, with no financial support, with no administration support, no nothing. Just women physicists volunteering their time and good heart decided to help other women, undergraduate women in physics who are in other places who need someone else, like a mentor. Michelle put a lot of time and work into a little bit of website development and that side of it. Her mom, Dee Knight, became a program administrator for free.
Wow.
And now, longest story short, I think we have around 300 mentees, 100 mentors. We have a long waiting list because unfortunately we cannot accommodate anybody. All over the map, if you go to our website, it shows the globe, and we have anywhere from Brazil, Argentina to India and other Africa, other places, women who taking part. And what we learned through this process, first of all, I learned a lot. This was a learning curve for me, like how to be a good mentor, what are your role as a mentor, you're not supervisor, you're not a counselor, what things can you do to help. But also we realized we are helping each other too, just connecting marginalized people to each other, having a network for them to talk to each other, not to feel helpless or alone and isolated. That by itself is a big step. A lot of times it's maybe a senior physicist asking another senior physicist, what did you do when you had this thing? If you are in part of this collaboration and things like this come up, how do you handle that? And so far working. We are growing quite fast, so we don't know. We are planning to maybe restructure it to make it more sustainable to accommodate the growth. But let's see how it goes.
It's amazing. Yeah. And so the mentees are mostly around graduate level?
No, they're mostly undergraduate, but sometimes master's students. So now we are thinking of restructuring it. Maybe we can do, so when we started, we would even have PhD students mentor undergraduate students. But now we are thinking, because as we learn, sometimes a younger postdoc needs a mentor from the faculty, or a graduate student could learn from a postdoc. So we might do a little bit of restructuring, but the original plan was graduate student and higher mentoring undergraduate. But then we started having even taking master's students. I have had master's students, mentees. Just recently, one of my mentees has, I have to brag about it. She's interviewing top schools in the world, has admissions.
That's great.
Oh my God.
Yeah. Sounds like the kind of thing that would have been helpful if it had been around when you were their age.
I think so. I mean, I know so many people, and broke my heart along the way that we lost, right? Because I make this analogy other places too. I'm saying this is for marginalized people, climbing the academic ladder is like a ladder which is constantly shaking. You keep losing people along the way, and I've seen it. I've seen it in my lifetime. So far in my career, how many we have lost along the way, that we would be fortunate to have still in academia.
And it's hard because this is such a big problem. I think so many people don't know where to start. And I just love what you said a little while back, that you can start with something that maybe seems small at the time. Now this has grown into something that's not at all small, but you started with something small that you thought would be helpful. And that can take you into something that can really make a big difference later on.
And I feel like it feels into, like, again, my personality. Like we discussed this, Niayesh is big picture, I'm going to change, and come out, I'm like, let's first focus. Let's see what I can do here and see how it goes.
But it takes both types.
Yeah, exactly. Both are very important.
Nice of you to say.
Niayesh, do you have like big picture ideas or
About well, and actually, I mean, Ghazal is the expert. I have a feeling. I mean, she's maybe we have a little bit of a role reversal, because I think Ghazal is she's also. I'm saying you're the president of the Women in Math in Waterloo, or
chair of the
chair of the Women in Math. So she has kind of the Supernova Foundation. I mean, I think it's a great. It's such a big project now, even though it's started small, and also all the stuff she's doing at the Women in Math in Waterloo, at the University of Waterloo. So I'm still at the level of helping 1% at the time. So I haven't really have as big of an ambition, but I try to do my best in this regard. Yeah,
that's amazing. Well, we have one more question that was sent in by another student, so maybe we can play that one.
Mm-hmm.
I'm Matt Duchenne, a PhD student at Perimeter. I'm wondering, what do you think each other's most interesting and exciting contributions have been?
We've talked about...
For the listener, they looked at each other and didn't answer the
Well,
question.
I'm laughing because I sometimes do these interviews, postdoc interviews, and this is what I ask.
Really?
No, I'm on the hot seat.
No, but you're supposed to say that about me, right? Or
Yeah.
is it,
Oh,
I
okay.
think that's the
I thought I was
question,
supposed to talk about myself.
Yeah, you brag about his contributions and vice versa.
or bad? It doesn't have to be brag. It's okay.
Yeah, I think that cross correlation. This is that was a thing that Niayesh was a pioneer in this era. Now it's like I mean, not that I'm saying echoes or things not gonna be as big, but I'm saying that one is now tested and grown, and I think it was a big contribution to the field, how we can extract some actual physics and separate these things out of such tiny signals in different parts of data, or completely different data sets, I guess.
Right.
Yeah.
And I don't even think we asked you about that, Niayesh, about these black hole echoes.
Yeah.
Do you want to tell us a little bit about that?
Sure. Yeah. And it's entirely not your fault. I do so many different things. Like each of them is like a black hole. But yeah, I actually did work on actual black holes as well. And no, this is so the story of echoes, which I think Ghazal was alluding to as maybe not the most exciting thing I do, but let me see. Maybe time will tell. So this has started with LIGO seeing gravitational waves around 5 or 6 years ago, which they won the Nobel Prize for recently. But in fact, it's amazing thing because it opened this door for us for looking deep into places where gravity is very, very strong, basically as strong as it gets. These black holes that we knew about them before, like for example from Event Horizon Telescope picture. You knew there's some place where gravity is strong, but it was very hard to get very deep because basically just light stops at some point. And gravitational waves actually can get deeper because gravitational waves are actually weakly interacting with matter, so they can probe very, very deeply into places where we know gravity should break, these singularities we were talking about. Mm-hmm. Now, whether they will actually get there, it's a matter of debate. But I actually, I've since LIGO discovered gravitational waves, I've thought about this problem a lot, and we've written papers on this with my students in the past 5 years or so. And I think it's kind of inevitable that if quantum mechanics is somewhere united with gravity at some point, then black holes cannot be these bottomless pits that basically general relativity tells us. So general relativity tells us that, black holes don't have any end. Basically, things fall in and keep going in, and it never really Nobody from outside will ever hear you hitting the bottom of a black hole. According to Einstein, that's a one-way street. But if you believe in quantum mechanics, it cannot be. So there should be a finite amount of space there. So eventually you got to hit the bottom and you're going to hear back. And those are the echoes that we've kind of been exploring for a while. And I think it's an opportune time because it's the first time you can actually hear black holes, but also hear them so deeply, basically, when they're forming, and basically you can see basically down into the very bottom of them. And we think echoes is a possible signature of what could be sitting at the bottom of the black hole, and a very opportunistic time to basically looking for this. I mean, there is no guarantee, but I think that's what I'm most excited about these days. So Ghazal has had a lot of interesting and influential works, but I mean, she talked about some of them. For example, how Coscuton could help us bounce, so the contracting universe could become expanding. But probably the most important, exciting thing is that she showed. I mean, the very early universe. At least one of the three tenets of physics, as we know it, should break down. It's either that you need to have negative pressure, that in inflationary phase like we do now. But if you don't do that, you either get propagation faster than the speed of light, or you need some quantum gravity effect, basically. So she actually proved a theorem to that effect. So it's a technical work, but it's a solid technical work in the spirit of the kind of thing that she does, that they're all she crosses all the T's and dot all the I's, so that there's no doubt left that that's what's happening. So if you think, so there are three possibilities, thanks to Ghazal, we know, in the early universe. Everything else people have thought about falls under those three.
I guess to explain, like empirically, we noticed it, that people are coming with these scenarios, but I noticed that they either fall into one of these three. And again, like me, I'm like, okay, why is that? There should be a reason for that people are coming up only with these three different possibilities.
So she proved a theorem that these are the only three possibilities.
Okay, so that's why it is happening.
Well, it's amazing. It seems like both of these contributions you're mentioning really speak to each of your strengths and your unique approaches to research. It's neat to hear.
Nice of you.
Well, I've enjoyed it.
Thank you.
Thank you so much for joining us. It's just been fascinating. And it's our first time talking to two people at the same time. And it's great to hear the two sides.
I feel like we've just scratched the surface of some of these topics, so we'll have to have you back another time.
Thank you. Thank you for inviting us. We enjoyed the conversation.
It was a lot of fun. Thank you very much for having us.